what I'm going to talk about today is some really, really good news that's coming out of the world of geroscience and aging, which you heard a little bit about moments ago. But you have to understand the background and the logic behind it in order to appreciate what's coming down the line and why it's so important and relevant in our world today. Now, this is based in part on testimony that I gave to Congress almost a year ago on this very issue of an aging intervention that I would suggest is going to be as important as the introduction of antibiotics in the middle part of the 20th century. So I think we're on the verge of a pretty important breakthrough, and the work that's going on here at UC San Diego is right at the forefront of this work in aging science, so it's extraordinarily exciting. All right, so these are the issues that I'm going to be addressing in order. I'm going to deal with this issue of hype and embellishment because there's a lot of information out there suggesting we're all going to live to 100, 200, 500, 1,000. Does anybody really believe this? But believe me, there are some people that actually believe it. I'm going to tell you, of course, it's not true, and I'm going to explain why. I'm also going to discuss the issue of human longevity, why it's predictable and why it's limited. It's related. I am going to provide what I refer to as the Faustian longevity bargain, which explains sort of how we got to where we are and where we're headed. And this is critical for understanding the work that's going on in geroscience and why it's so important. And then I'm going to briefly touch upon, I'm going to show you a couple of videos at the end where some colleagues of mine and I met with the Food and Drug Administration, with the FDA, on some interventions that are being worked on to slow aging. But this is groundbreaking work, and I believe it will come in line to influence hopefully most of the people in the room today. So let's deal with the hype first. There's stories that come out there all the time about how long we can live, whether we can live to 100 or 120. There's a great misconception here because there's a lot more centenarians, right? A lot more people making it to 100, 90, and 80, but life expectancy is leveling off or declining. They're not really closely related to each other, contrary to popular belief. So we will experience, in all likelihood, a leveling off of life expectancy, but perhaps even a decline for reasons I'm not going to get into now, but the size of the older population is going to rise dramatically, no matter what. That is a demographic certainty. Many of us in the room are part of that process. Living to 120, this came out in National Geographic. You're going to see the numbers get higher and higher. So this came out in Time magazine, 142. I get a kick out of it. Any number over 122 is made up, right? Because we had one person that made it to 122. So when people make up numbers, I'm not really a big fan of that. It's not science. Unfortunately, a lot of what's out there is not science, and you need to be able to distinguish between the non-science and the real science. The real science is happening here at UC San Diego. There's a big difference. This is a good one, the Forever Pill from Bloomberg, 173. So don't you ever wonder how they make up these numbers? It is a made-up number, 173. I'm sorry, it's just not going to happen. You may not even want it to happen. Making it to 173 in these bodies the way they are now, yeah, it's not going to work. It's the components of the body weren't designed to last that long. So, yeah, that's just not going to happen. It doesn't have to happen in order for us to really understand and appreciate all that's going on in the world of aging. So why is longevity predictable? You're going to get a dose of science here, and it's really critical to understand why it is that we live as long as we do. So you're going to walk out of here knowing the answer to this question. So this particular image, this figure was generated by an actuary in 1825 by the name of Benjamin Gompertz. It was an answer to a simple question because they were trying to figure out how much to charge people for life insurance. So how do you do that? Well, you calculate what the risk of death is. And they actually didn't know what the actual risk of death was as a function of age until Gompertz came along and showed us. Now, this is a semi-log scale, which means when you see a straight line, it means an exponential increase in the risk of death. This isn't rocket science. The older you get, the higher the probability of death. No, you know, you're laughing at this, right? But I'm doing 3 interviews a week right now on whether or not there should be an age limit on being president of the United States. So I am getting this question all the time. So this was an observation by Gompertz in 1825, pretty important observation. This is an image I use to explain what happens to us as we grow older. So this was a painting that was commissioned by a statistician by the name of Carl Pearson. You might recognize that name if you've taken a class in statistics. This is Pearson correlation. Pearson in 1897 was observing what death rates look like, pretty much what the Gompertz curve showed you a moment ago. I'll show you a picture of what Pearson was basically seeing. But these skeletons represent death or the force of mortality, and the people crossing the bridge represent people at different ages. So you could see the infant about to get bashed over the head by the force of mortality, implying infant mortality was extremely high. The point of lowest mortality is always at puberty in humans and other sexually reproducing species, and then the risk of death rises exponentially after that, which is what Gompertz showed in 1825. Take a look at the force of mortality way over on the right with the rifle, right? Not even looking at his target. And what that implies, and you notice there's no crossing that bridge, which implies that there's a limit to how long we can live. And of course, you don't have to pick off individuals at older ages with heart disease, cancer, stroke, and Alzheimer's because aging is going to get them anyway. That was the message that Pearson was trying to get across, that aging is inevitable. And you know, I don't think that anybody doesn't know that aging is inevitable. Well, maybe except for some of my colleagues in the field of aging who think we can live for 1,000 years. And I would say, of course, that's possible if we overcome the second law of thermodynamics. For reasons that I'm not going to explain now, we're not overcoming the second law of thermodynamics anytime soon, so we are not going to be living to 1,000 in these bodies. This is what basically Pearson was looking at. What do you see here? High infant and child mortality. Point of lowest mortality is always at puberty. I've written extensively on why this is the case, by the way, and then the risk of death rises exponentially thereafter. There's Gompertz's line. The risk of death has gone down, but the age trajectory of death in humans has never changed in recorded history. You see the exact same curve for other sexually reproducing species. What's happening to us is happening to your dogs, your cats, elephants, horses, basically almost all living things in exactly the same way. So why does death occur with such regularity? I use a race car analogy to explain why this happens to us, and this should be easy for everybody to understand because we're all experiencing this. I use an Indianapolis 500 race car analogy where, you know, the engineers build these cars to last for 500 miles, but if you continue to run them around the track until they all failed, you would see things go wrong with these cars that you ordinarily wouldn't have an opportunity to see because you shut the engine off at 500 miles. So the things that go wrong out here aren't engineered by the engineers. The engineers were interested in survival, not death. So they wanted to make sure they made it for at least 500 miles. In sexually reproducing species, the story is pretty much the same. We need to make it, we go from a fertilized egg to a teenager, to a reproducing adult. We ensure the reproductive success of our offspring by making it to grandparenthood. I could say I'm at 2.5 now. The half of one is 20 weeks in. And what have we done during the course of the 20th century? We've pushed out the envelope of survival into the post-reproductive region of the lifespan where we get to see things go wrong with our bodies that we wouldn't ordinarily have an opportunity to see. Surprise. It's not exactly unknown that this was going to happen, that we were going to see heart disease, cancer, and stroke, and these things that appear at later ages. Keep in mind, this is not our fault. It is not your fault that you get heart disease, cancer, and stroke, and Alzheimer's. It is a byproduct of surviving long enough to experience them. Now, can we accelerate the probability that these things happen? Of course. We're really good at it. We're masters of it here in the United States, of acquiring risk factors that shorten life. But once you control those risk factors, you can push out the envelope of survival, but the question is how much further can you push it? So again, what's going on out here is an accident of living long enough to experience the consequences of aging. So here's an example that I like to use to illustrate the relationship between these attributes of individuals and duration of life. I'll talk a little bit more about this in a moment. But a mouse, for example, goes through puberty at 30 days, and it lives about 1,000. A dog, this was my dog, Sophie, they go through puberty at about 9 months. They live about 5,000 days, depending on the size of the dog. Smaller dogs live longer. Elephants live about 26,000 days. Humans, we go through puberty at about 11 to 12 years of age. We live about 29,000 on average. Sea turtles go through puberty at 50 years of age. That's 50 years of age. They live for 150 years. A bowhead whale can live for 210 years. I honestly don't know when they go through puberty. This is my favorite, a Greenland shark. Greenland shark goes through puberty at 150 years of age, and they can live for upwards of 500 years. So duration of life of humans and other sexually reproducing species is calibrated to something that has nothing at all to do with our lifestyle. It's calibrated to the onset and length of the reproductive window of the species. When we go through puberty, when we go through menopause, these are genetically fixed attributes of the species. We are not modifying that anytime soon. It doesn't mean that any of the previous information you heard about the importance of lifestyle modification doesn't work. It does work for reasons that I'll describe in a minute. But you're not going to get radical life extension by manipulating fertility or menopause anytime soon. And I do expect some questions about menopause, so feel free to ask. So here's I probably should have shown this slide first. So this shows the relationship between the force of natural selection and reproduction. Look, forget about all the words for the moment. Just take a look at this. I divided the human lifespan into 3 regions: the pre-reproductive region, the reproductive region here, and the post-reproductive region of the lifespan. So as soon as a species begins reproducing, the ability of natural selection to influence genes begins to decline. Once we get out into the post-reproductive region of the lifespan, where most of us in this room are, natural selection is no longer operating, which means there's no penalty for carrying genes that do harmful things later in life. Basically, natural selection doesn't care about us at that point. We've already passed our genes on to the next generation. So again, duration of life is calibrated to this window here between puberty and menopause. This is the reason why the risk of death is always lowest at puberty. It's a long, long story, but it's an evolutionary explanation. It is an invariant attribute of the species. I shouldn't say that. It's not quite invariant. Early in the 20th century, puberty in humans for females was about 18 to 19. And the reason had to do with body fat. There was malnourishment back in the early part of the 20th century. And we are witnessing today, now that I think of it, some unusual attributes in the opposite direction, where we are getting some of these extremely obese young children that are experiencing puberty at 7, 8, 9 years of age. So we are manipulating this to some extent, but I don't know if it's having an impact on duration of life. So I use this image because I was a runner for many, many years until I developed spinal stenosis. And I tried to run a 4-minute mile in my younger days. I really thought it was possible. I just said, brain, make your legs move faster. So I went out on the running track and I conveyed the message to my legs, but it didn't work. And so the reason it didn't work was because this particular body design that I have isn't going to allow me to run that fast, even though I thought it was theoretically possible. In my head, I knew it wasn't going to work, but I figured I'd give it a try. For the same reason, we can think all we want about living to 120. I've even read a book by somebody who said, I've decided to live to 120. I'm going, yeah, well, You can decide all you want, but Mother Nature, will step in and probably influence whether or not that's possible or plausible. But it's basically a way of saying there's no gene that says I can't run a 4-minute mile, but my body design won't allow it to happen. There's no gene that says you can't live to 120, 130, 140 in theory. There's no limit. There's no genetically based limit, but in these bodies, it can't happen. Aging or senescence I view as a byproduct of surviving beyond what I think of as our biological warranty period. So let me explain the entire line of reasoning behind geroscience, because this is really important work. It's really exciting. And I'll describe some potential breakthroughs in a little bit. Again, this is, if anybody wants to see the testimony or the written testimony from last year, I can provide a link, but it actually, the congressmen were very attentive and they knew exactly what we were talking about. They got it. Yeah, that's right. You're right. They're all old enough to recognize that this, this is happening to them. You're right. So my colleagues and I published an article on this in 2006 entitled In Pursuit of the Longevity Dividend. Longevity dividend was the word that my colleagues and I came up with. It means geroscience. It is virtually exactly the same thing. The co-authors, by the way, for those of you who know, Bob Butler was the founding director of the National Institute on Aging. Rich Miller is at the University of Michigan. Dan Perry was with an organization affiliated with aging science. So here's the line of reasoning. I'm going to go through this fairly quickly. And if any of you are familiar with the story of this is Goethe's Faust, right? So you know the Faustian bargain. There have been lots of books and movies about Faust. And when you look at human aging and longevity from the perspective of a Faustian bargain, it all makes sense. So think of it this way. Mephistopheles, which was the devil in the story of Faust, came to us 150 years ago and said, I've got a deal for you. The deal is I'll let you save your children. Right? You have very high infant, child, and maternal mortality. I'm going to allow you to save them. And you're going to get 30 years of an increase in life expectancy as a result. You're going to go from 50 to 80. That's exactly what happened during the course of the 20th century. We went from 50 to 80 in today's developed countries. And we signed the papers. I would have signed the papers if I was there in 1850. What a great deal. We save our children. Most of us have an opportunity to live a long life. And definitely a good deal. If I was there, I would have signed the papers for sure. This is a metaphor because when you consider the Faustian bargain today, it's a different ballgame that we're playing than the one that we played more than 100 years ago. So Mephistopheles is here. Oh wait, that's the first author. So the price that we had to pay. So you remember the Faustian bargain is always about a deal that sounds good at the beginning, but you eventually learn is a bad deal later on. So the Faustian bargain was, you could save your children, but most people now are going to live long enough to get heart disease, cancer, stroke, and Alzheimer's. I still would have signed the papers. The privilege of living a long life is basically what was being offered to us. And it's a good deal. I'm 69 years old. I'm happy to be here. The vast majority of us in this room, by the way, would not be here if not for the advances in medicine and science and public health that happened during the last 100 years. So we are a living byproduct of that first bargain from about 1850. Well, Mephistopheles is here again offering us a new deal. The new deal is I'm going to allow you to make progress against the diseases that I gave you 150 years ago, which are expressed in later regions of the lifespan. But sorry, you're going to get a much smaller increase in life expectancy or longevity than you got before. You're not going to get 30 years anymore. And there's going to be some trade-offs. There's likely to be a reduction in the risk of death from heart disease, from cancer, from stroke, but be careful what you wish for, because death is a zero-sum game, and when you reduce the risk of death from one disease, something else must rise. You may not like what rises as a result of cures for cancer and cardiovascular disease. Now, don't get me wrong. I'm not saying we shouldn't be trying to go after these diseases. We should. I'm just telling you that at the population level, if we succeed and we don't manipulate aging in any way, we may not like what we see. And I would suggest that we are there right now. So here's the entire logic and line of reasoning behind geroscience in a nutshell. So I'm actually going to do in about 2 minutes here what would normally take about an hour in a lecture and a manuscript about that thick. Let me run through this just to give you a sense of what this is. And there's some basic evolution biology applied here. So as it turns out, if you go back and study evolution and evolution biology, you realize that the timing of reproduction for every species is calibrated to the hostility that that species faces in the environment. So you remember that mouse that I showed you? Well, a mouse is a meal for a lot of different other animals. So they better start reproducing pretty quick, otherwise they're gone, right? So that's why they go through puberty at 30 days and they start pumping out, baby mice pretty quick. It makes perfect sense. So animals that face a low hostile environment, like those Greenland sharks, can delay puberty and experience a long reproductive window and live very long lives. The programs that influence all of that, growth, development, reproduction, those are fixed genetic attributes of the species. Those are not changing anytime soon, and we probably would not want to change any of those without grossly manipulating what it means to be human. So duration of life is calibrated to something that has nothing at all to do with how we live our lives. That's sort of rule number one. It doesn't mean we can't shorten our life. We can. We're really good at it. But the question is, how much longer can we live by adopting these healthy lifestyles? So aging is an accident of these fixed genetic programs. In longer-lived populations, aging, the biological process of aging, then becomes the most important risk factor for the things that go wrong with us as we grow older. You have to realize how important it is to understand that there is a barrier there, the basic process of aging that all of us are experiencing, which is why geroscience is so interesting and exciting. So if you only extend life by lowering the risk of major fatal diseases, we run the risk of increasing frailty and disability among the surviving population. I'm going to show you one image to illustrate this whole point momentarily. So I said this already, death is a zero-sum game. It's a set of trade-offs. We predicted way back in 2005 in this New England Journal of Medicine article that life expectancy was going to go down as a result of childhood obesity, and it did. Shortly after we published this, I think it was 5 years after we published it, the decline started about 2010. We thought it was going to wait until 2015, but we were wrong. So the prediction that some of us have is that we're on the verge of a pretty dramatic accelerated increase in Alzheimer's disease, neurological problems, components of the body that aren't replicating. So the muscle fibers, the neurons in the brain, these are our Achilles heels. These are the parts of the body, it's sort of the reason why I couldn't run a 4-minute mile. These are the reasons why we're not going to live, 150 to 200 years. We have parts of the body that weren't designed to last that long. So that's sort of the logic and the rationale behind the longevity dividend. My colleagues and I published a book in 2015 on this topic. I'm pleased to say that in the first quarter of next year, our next book is coming out on this, on the latest developments, co-authored by the same authors, George Martin and Jim Kirkland. Jim Kirkland's at the Mayo Clinic. George Martin was at the University of Washington. Unfortunately, he passed away last December. The book is dedicated to his brilliance, but we're real excited about this new book coming out. So this is what's being taught in the world of aging science today. I'm going to go through some of these pretty quick. These are the risk factors for heart disease. This should look familiar. Fundamentally wrong. The most important risk factor for heart disease is the biological process of aging. This is what we've been taught about cancer. Fundamentally wrong. The most important risk factor for cancer is the biological process of aging. This is what we've been taught about Alzheimer's disease. Fundamentally wrong. Aging is the most important risk factor for the things that go wrong with us. We are playing a different game than the one that we played 100 years ago. Aging has gotten in the way. It's what we wanted. I mean, we wanted to live long enough to experience aging. Now, this image here is the one image, so I published this in JAMA in 2018 from Lifespan to Healthspan, where I suggested everything that you're talking about here at UC San Diego about focusing in on healthspan is what we should be doing in the world of public health and aging science today. It's not length of life that's important, it's quality of life that's important. So I use this image as a way to illustrate this. By the way, right after I show this, I'm going to show these brief videos, and then I'm going to stop and take questions. This is what's called the distribution of death in the life table. You can see high infant mortality. This is maternal mortality for females in 1900. This is what the distribution of death would look like for 100,000 babies born in a given year. So it's pretty illustrative of the timing of death in humans. And you could see during the course of the 20th century, we redistributed death from the young to the old. We brought down early age mortality. We shifted the death curve out to these later ages, to this blue line. And this is what we've done to ourselves. This is the Faustian bargain, right? We've got heart disease, cancer, and stroke as a result. If we continue to go after major fatal diseases one at a time as if they're all somehow independent of each other, we're zeroing in on trying to push out this blue line. That's what the disease model is all about. What geroscience is all about is to push back the red zone, what I refer to as the red zone, the time period when frailty and disability is common at later ages. We're not trying to make people live longer. We probably will, but I don't know by how much. Those are my three favorite words that I tell my students to use all the time. I don't know, and that is because we don't know how much longer we will live if we slow aging. But what we do know is that we will likely live healthier longer as a result. And in the end, that's all that we're seeking. Now, the red zone is easy to understand, especially if you're from Chicago. You won't understand this if you're from San Diego. Now, the reason is now, at least up until yesterday's football game for the Chicago Bears, once the Bears get down to the 20-yard line, it's almost, at least until yesterday, almost impossible to score a touchdown. And the reason is that all the defenders are located in a very small space, about 20 yards, between where they are and where the end zone is. It just gets harder and harder to push the football. That's the concept of the red zone. Don't think of this as a brick wall. It's not a brick wall that says you can't, live longer. Just think of it as an increasingly more dense forest of aging and aging-related diseases that we are pushing up against. And so the longer we live, the more dense this forest becomes. We're there already in today's developed world. We are in the forest. So we are not going to easily make ourselves live a whole lot longer, but we certainly have the ability to compress this red zone. Now, I'm going to show you two brief videos, and then I'm going to stop and take questions because I realize I'm running out of time. These two brief videos, one of them shows my colleagues and I meeting with Senator Claire McCaskill in 2016, I think, to discuss some of these issues. This was at the this was during the Obama administration, near the end of his second term. And President Obama was considering this geroscience initiative that we're talking about here as one of the global challenges in health that he was considering. He ended up using the cancer moonshot instead, which we said, well, if you slow aging, that is the cancer moonshot. But it was not easy to get through. But let me show you these videos.
If they can win support from the highest reaches of government, scientists believe they can change our nation's outlook on aging. They meet with the ranking member of the Senate Aging Committee to make their case.
What people don't realize is we have found a way to intervene with aging, and these concepts have been proven in animals and is now going to be tested in humans. the major risk for any one of the diseases is aging.
If we can get a handle on slowing the aging process, if we could actually do that, we are talking about a huge economic boon to this country.
Every major public health advance in the 20th century had a champion, somebody who stood up and said, I want this to happen, I'm going to make it happen. And we're hoping that sometime before the president leaves office, he raises this issue once again, considers it a global challenge.
Well, I'll be glad to tell him.
We would be delighted.
Yeah, I will be glad to tell him.
There's a lot of excitement in the field now, and we feel traction. We can feel it. We can sense it, that people are coming on board.
So there's been about correct me if I'm wrong, but I think over a $4 billion investment in aging science just within the last few years. Certainly since this video came out from National Geographic. And the next one that I'm going to show you is where the breakthrough happened when we met with the FDA. But there's been a huge investment in this world of aging science. You're witnessing some of it here, of course, at UC San Diego, where much of the money is coming. And I'm delighted to see whatever it is that you're working on, if it's mitochondrial aging or some other component of aging, they all need to be pursued. We don't really know which one of these interventions is going to work, but there's lots of pathways that researchers are pursuing that will allow us to slow this biological process. Keep in mind, this is not hypothetical. This is not theoretical. It has already been done in other species. It has been accomplished. And keep in mind, you can actually witness variation in the rate of aging just by looking around the room. There are people that experience biological time at a slower rate today. Those that are making it out into their 70s, 80s, 90s, 100, especially those that are making it out to extreme old age, are probably experiencing biological time at a different rate than the rest of the population. What does that mean? It means the clock is ticking more slowly for you. While you might be 80 years old, I'm not pointing to you in particular, but while you're more like 60, but while you might be 60 years, while you might be 60 years old, chronologically, you've gone around the sun 60 times. Biologically, you might be 50 or 45. So the clock may be ticking for you. And this is one of the answers that I give when I'm asked about Trump and Biden, for example, and whether or not there should be an age limit. I'm going, yeah, biological time is probably ticking differently for them. There's a subgroup of the population known as superagers that are individuals that can make it out past the age of 80, that are cognitively intact, operating at a very high level. Let me show you this last video, and then I'm done.
Today, Dr. Barzilai and his colleagues will try to convince the FDA to consider their study. In advance of their critical meeting, they gather to prepare.
I really want to frame the discussion today as what would we need to show in a clinical trial that would allow the FDA to approve a new indication for metformin for delaying multiple morbidities related to aging. Because we think metformin is the first one, but there are others that could be better than metformin, and we want to make sure that that's the template.
It started with a conceptual innovation that aging can be modified. Then years of work by a growing number of scientists in labs around the world, and years of convincing people of their ideas. Maybe this is what a breakthrough looks like.
I don't think that there are too many interventions in history that would rival the type of intervention that we're talking about here. It would influence almost everyone.
If you really are doing something to alter aging, the population of interest is everybody. It surely would be revolutionary if they can bring it off. There's no doubt about it.
We always thought that the promised land is not in our reach. And I think that we are going to the promised land. The study will happen. The fact that the FDA is going to be part of it is really a major achievement, and eventually will be the template and affect health span in the next decade.
We weren't really sure how the FDA was going to respond. Senolytics is one of the potential therapeutic interventions that's being worked on, It's an effort to remove cells in the body that are still alive but not doing what they're supposed to be doing. So there's an intervention that's in, I don't remember if it's phase 1 or phase 2 clinical trial right now at the Mayo Clinic to remove these zombie cells. Now, I hesitantly use the word reverse because there's evidence to suggest that some elements of aging has been reversed in some of these animal models, but generally I don't like using that word because we're not going to transform you into 20-year-old versions of yourself. I wish we could do that, but you may not want to be the 20-year-old version of your, well, wait, maybe you would physically want to be the 20-year-old version of yourself, but maintain all of the knowledge that you acquired during the course of life. So, all right, but second law of thermodynamics is going to get in the way. It's not going to happen, but can we make ourselves healthier longer? Absolutely, yes. And I'm going to end with this, and I would be delighted to take any questions that you have. So thanks for your attention.
Thank you so much. What a fantastic talk. Thank you so much. Okay, we're collecting cards. We only have a few minutes for Q&A. I'm so sorry about that, but we're going to jump right in, Dr. Olshansky. Is the rise in the use of artificial intelligence influencing the study of aging, and if so, how?
I don't know. My three favorite words. I don't know the answer to that yet. It hasn't influenced duration of life yet. Is AI, does it have the potential to influence duration of life? Maybe. It may influence, you may have a better answer to this than I do, but it may influence the treatment of specific diseases more effectively. Others may have better answers to this than I, but the answer is I don't know. Certainly we're not seeing it yet.
Okay. How is the replacement of human body parts with mechanical computerized parts, does it affect our life expectancy? So like knee replacements and things like this. Does that impact life expectancy?
Probably not much. So for example, you know, we've created all of these props, right? So I have one here, right? Many of you have these, right? I have these here, my hearing aids. Right, so these are all things that we've done to ourselves that allow us to overcome these. I mean, they're just nuisances now, right? And so many of my friends have had problems with their knees, their hips. They have them replaced. Those become nuisances. Now, if we become immobilized as a result of problems with our hips and knees, like our, you know, from a few generations ago, and you become sedentary, yes, I suppose under those conditions, it's going to shorten your life. But as you heard earlier today, movement it's like an oil, lube, and a filter for your body, you know, for your car. It works. It actually has a positive impact. You can improve your health and quality of life by exercising at any age. You can be 100, and it's cheap. It's free. The benefits are instantaneous, and it works. It may not necessarily let you live a whole lot longer, but in the end, we're not trying to push out that blue line. We're trying to compress the red zone, and all of these interventions are really designed to do that, is to compress the red zone.
Can you address your thoughts on why some younger ages experience cancer, Alzheimer's, things like this? So early onset Alzheimer's, dementia.
Genetic heterogeneity. So it's one of the reasons why, just because Jean Calment lived to 122, it's the reason why we cannot expect the rest of us to live that long. It's the same reason why one person ran the mile in 3 minutes 43 seconds. We can't all run a mile in 3 minutes 43 seconds because of the genetic diversity that exists in a population. So inevitably, you're going to lose some segment of the population at younger ages just due to congenital anomalies, but just basic genetic variation that exists. It's a combination of inherited and acquired risk factors that are influencing what's going on. So it's inevitable that you're going to have a distribution. Some long-lived individuals, some people inevitably will die early. You remember the story of Jim Fixx, right? He died in his 50s from hypercholesteremia. He basically brought running to our consciousness a while ago. And then you have, by the way, Jean Calment, you're probably not aware of this, but she smoked for 100 years. That's not a license to smoke. Most people that smoke are going to die earlier as a result, but it tells you that it's not necessarily a risk factor for everyone. The same with obesity. older individuals that carry some excess weight actually benefit from their excess weight. I remember having this conversation with my mother when she was 85 years old. We were out to dinner. She was trying to decide on whether to have dessert, and she was saying, "Oh yeah, I have to watch, my diet. I need to lose some weight." I'm going, "Mom, if obesity was a risk factor for you, you'd be dead already." I said, enjoy your dessert. Just don't, overdo it. And she really enjoyed her dessert that night.
Wow, on that note, I'm going to say thank you, Dr. Olshansky, for such a great talk today.